Projection radiography provides a static, high-resolution snapshot of human anatomy. Fluoroscopy operates on a different priority. It sacrifices that fine spatial detail to achieve the continuous temporal resolution required to see internal motion as it happens. Diagnosis requires observing physiology in action, the mechanical pumping of the heart, the expansion of the lungs, or the flow of contrast. But observing internal motion using X-rays carries a severe biological cost. Regulatory standards strictly cap the maximum entrance skin dose rate for a patient at 100 milligrays per minute. This creates a difficult constraint. Firing high-dose radiographs at video frame rates would be lethal. Conversely, lowering the continuous dose to a safe level produces a signal so weak that the resulting image is swamped by noise and completely unusable. To safely peer inside the body in real time, that low-dose X-ray signal must undergo a massive physical amplification process before it ever reaches a display monitor. By the late 1950s, this was achieved through the image intensifier tube. These systems are characterized by their extreme bulk, often dominating the space above the patient in the clinical room. The demand for real-time visualization forced the invention of this complex conversion engine, prioritizing extreme signal amplification to protect the patient from high radiation exposure. The image intensifier operates within a vacuum environment, encased in a glass or ceramic envelope. A metal housing surrounds the entire assembly, shielding it from ambient light and external magnetic fields that could interfere with the internal signal. The X-ray beam enters through a convex window. This is typically made of aluminum or titanium foil, low atomic number metals that allow the beam to pass through with minimum attenuation while maintaining the tube's vacuum. Once inside, the photons strike the input phosphor, a layer of sodium-activated cesium iodide. This layer is channeled into needle-like crystals, only 5 micrometers in diameter. These crystals act like fiber optics, capturing up to 90% of the X-ray energy while preventing light from spreading laterally and blurring the image. The first stage of amplification happens here. Each absorbed X-ray photon produces approximately 3,000 light photons in the blue spectrum. This blue light is immediately absorbed by the adjacent photocathode, an antimony cesium alloy specifically tuned to this light frequency. Through the photoelectric effect, the photocathode releases a pattern of electrons into the vacuum, roughly 200 electrons for every original X-ray photon. By translating invisible X-rays into a highly organized cloud of electrons, the system creates a physical medium that can now be electrically manipulated and magnified. To amplify this signal, the system maintains a massive 25 kilovolt potential difference between the negative input screen and the positive anode at the output. Positively charged focusing electrodes along the tube walls constrain and guide the electron cloud, accelerating it toward the output stage. This process achieves minification gain, which is mathematically the square of the input diameter divided by the square of the output diameter. By compressing the same number of electrons into an area 1/10 the original size, the system significantly increases the brightness of the resulting image. Simultaneously, the high voltage adds kinetic energy to the electrons, creating flux gain that further multiplies the signal strength. Together, these two factors provide the total brightness gain of the tube. In clinical practice, physicists use the conversion factor to measure this ability, linking the luminance of the output screen directly to the entrance dose rate. This physical relationship impacts patient safety. When using the electronic zoom to sample a smaller input area, minification gain falls. The image becomes darker, forcing the system to drastically increase the radiation dose to maintain a visible image. The image intensifier does not create new data. It exploits high-voltage electrostatics and geometric compression, turning a whisper of an X-ray signal into a shout. The high-speed electrons eventually reach the output window, which is coated with a thin layer of opaque aluminum. This aluminum layer acts as the anode, while blocking light from reflecting backward toward the photocathode. This prevents halation, which would otherwise degrade the image contrast. The electrons strike silver-activated zinc-cadmium sulfide crystals, completing the final analog conversion back into visible light. In modern systems, this light is captured by a charged couple device, or CCD, which has largely replaced the older, less efficient electronic TV camera tubes. The intensified light photons are absorbed into the silicon substrate of the CCD's light-sensitive array. This creates electron-hole pairs. Negative electrons accumulate in potential wells at each pixel in direct proportion to the light intensity, creating a zero-lag digital signal. This step bridges the gap between atomic physics and digital display, converting an intense light reaction into a self-scanning digital array. Despite its power, the vacuum tube has inherent flaws: a massive physical footprint, geometric distortion from the curved input window, and lost coverage in the corners of its circular field of view. These limitations are solved by the solid-state flat panel detector, which is rapidly replacing the image intensifier as the clinical standard. This architecture utilizes a thallium-doped cesium iodide scintillator superimposed directly onto an amorphous silicon active matrix. This provides a true rectangular field of view with better corner coverage and zero geometric distortion. Furthermore, flat panel detectors capture and convert signals 10 to 20% more efficiently than older systems, a metric known as detective quantum efficiency. By eliminating the vacuum tube, flat panel detectors provide a purely solid-state path from photon to pixel, raising the ceiling on image quality. That efficiency gain translates directly to the patient, allowing for a proportional reduction in the required radiation dose rate. To manage this dose, automatic brightness control continuously modulates the X-ray tube's voltage and current, maintaining a stable image across different tissue thicknesses. Operators select minimum, standard, or high-dose modes, balancing the highest image quality against a strict radiation penalty for the patient. Clinical staff must minimize dose through mechanical means, using tight collimation, increasing distance to the X-ray source, and removing anti-scatter grids whenever possible. Specialized procedures like digital subtraction angiography isolate specific anatomy by mathematically removing the background. To achieve this level of clarity, the dose per frame is pushed 1,000 times higher than standard fluoroscopy. To mitigate these risks, digital processing tactics like last image hold and pulsed fluoroscopy algorithms are used to limit total exposure time. Whether utilizing the intricate vacuum physics of an image intensifier or the solid-state efficiency of a flat panel detector, clinical fluoroscopy remains a physical balancing act between achieving spatial clarity and managing radiation risk.